All right, let's jump right in. Today's explainer is looking at something absolutely fascinating, a real-world, hands-on citizen science experiment dealing with plant life cycles. We're going through some documented gardening notes from a grower named Ang, and honestly, it's just a fantastic example of everyday problem solving. So let's get into it. So, can you actually cheat a plant's life cycle? It's a pretty bold question, right? I mean, out in nature, there is a very strict biological clock. A plant grows, it reproduces, and then, well, it usually declines. But what if you could intervene? What if you could literally hit a biological reset button and extend that plant's lifespan way beyond its natural endpoint? That is exactly what our source material is attempting to do today with a Coleus plant.
Section 1. The Coleus Life Cycle.
Okay, to figure out how to cheat the system, we first need to understand the baseline problem. Ang's gardening notes include this direct quote, "sending up tall spikes of purple and blue," end quote. Now, that sounds beautiful, right? But for a Coleus grower, this is actually a massive red flag. You see, Ang didn't prune the Coleus in time, and that caused it to bloom. And those beautiful spikes of purple and blue flowers, they're basically a biological alarm bell ringing, signaling that the end of the plant's life cycle is rapidly approaching.
And this perfectly illustrates the cost of that blooming phase. On the left, you've got the ideal state, those vibrant, colorful leaves. This is exactly what Coleus plants are famous for. But, as the notes point out, once the plant shifts its energy into making those flowers and seeds, you get the result on the right. The plant just stops producing those beautiful leaves and instead gets all scraggly and leggy. All that energy is completely redirected. Now sure, some varieties keep growing a bit despite the flowers, but generally speaking, the plant is in a state of deep decline.
Section 2. The propagation solution.
So, since the original plant is looking pretty scraggly and the window to harvest seeds was totally missed, taking cuttings is basically the last hope to save this thing. But here's where it gets interesting. Ang isn't just settling for the standard propagation methods. No, Ang is treating this like a true science experiment, testing exactly two distinct experimental tweaks to the normal process to see if they can guarantee success. Let's break down exactly what these two interventions are.
Section 3. Approach 1. Rooting hormone.
Right, so our first experimental hypothesis relies on a chemical intervention. Normally, a gardener might just toss some cuttings into a glass of shallow water and kind of hope for the best. But look at the precise methodology Ang is using here. Step 1. The cuttings get a full 24-hour soak in a rooting hormone for a very deliberate chemical kickstart. Step 2. They're moved into a jar specifically noted for having good moisture. And finally, Step 3. They're placed in adequate indirect sunlight. It's a highly controlled environment designed to literally force root growth.
Section 4. Approach 2. Oxygenation.
Now, to understand why this second mechanical tweak is so incredibly clever, we need to talk about why cuttings usually fail in the first place, and it comes down to anaerobic conditions. According to the reading, when you just leave cuttings sitting in stagnant water, the oxygen gets depleted over time, which creates a low oxygen environment, and that is exactly what causes devastating issues like root rot. So how is Ang solving this? Well, by grabbing an air bubbler from a nearby fish tank and piping those bubbles directly into the propagation water. It keeps the water constantly oxygenated. I mean, it's just a brilliant out-of-the-box fix.
And the supposed benefits of this aquarium bubbler hack are actually massive. According to the notes, this continuous oxygenation should speed up the propagation process itself, and like we just talked about, it physically prevents the anaerobic conditions that cause root rot. But it also gets incredibly practical, right? Because the water isn't going stagnant, it entirely removes the need for those constant, tedious water changes. All you have to do is just top things off as the water naturally evaporates. It's a super efficient, labor-saving setup.
Section 5. Awaiting the results.
Okay, so we've got our problem, and we have two very different, very clever experimental solutions. Let's just look at this side-by-side summary to really solidify the science happening here. Approach 1 is that 24-hour rooting hormone soak, which provides chemical root stimulation. Then, approach 2 is the aquarium bubbler, providing a mechanical solution to prevent anaerobic root rot. Both of these are designed to solve the exact same problem, saving the scraggly Coleus by extending its life cycle through cuttings, but they are attacking that problem from entirely different scientific angles.
Which leaves us with the ultimate question. Which tweak is going to save the Coleus? Is the chemical kickstart of the rooting hormone going to prove to be the most effective? Or will the continuous mechanical oxygenation from that aquarium bubbler create the absolute perfect environment for explosive root growth? Ang noted that it's going to be really interesting to evaluate how these small tweaks actually fare in the coming weeks. And honestly, I kind of can't wait to find out either. Think about the plants sitting in your own home right now. Which of these methods would you bet your money on? Anyway, thank you so much for joining me for this explainer. Keep asking questions, keep experimenting, and I'll see you next time.